Now let's talk about finding derivatives of functions that have two variables. Remember that when we were working with functions of a single variable like y is equal to f of x, when I took d by dx, or the derivative with respect to x of y, that was equal to the derivative with respect to x of f of x, so that the derivative with respect to x is a rate of change associated with the slope of a tangent line at a given point on the curve. We can also take the derivative of a function that involves multiple independent variables by taking the derivative with respect to any of the independent variables on its own. When I do that, these derivatives are called partial derivatives. They still represent rates of change and involve the slope of tangent lines. So we need to think a little bit about what the slope of a 3D surface might be like. Suppose I've got a lost hiker who is trying to describe a saddle in the mountains that he is stranded on by radio to a search and rescue team. They want to know how steep the slope is in the area he's located in order to know if they have the right equipment to reach him. So I have my hiker lost in a little saddle in the mountains that I've represented by a hyperbolic paraboloid type curve on an XYZ coordinate system. As my hiker examines the terrain, he realizes that depending on which way he looks, the slope is going to be different to reach the point where he's standing. What he tells the search party is going to depend on which direction the search party has to come in from in order to rescue him. This is an indication of the fact that when I talk about slopes of 3D surfaces, I have to be very aware of exactly what path I'm taking along that surface to determine what the slope is. If I move along a surface described by z is equal to f of xy, starting at some point that I'll label a, b, and f of ab, in such a way that only the x value changes. In other words, I'm going to hold y fixed at the value b, and then we're going to determine the rate of change along the path where only the x is changing. If I do this holding everything but x constant, it's simply the process of taking an ordinary derivative of the function f of xb with respect to x and be done. But I don't call this a direct or ordinary derivative. I call it a partial derivative because we are forced to hold one of my independent variables constant in order to do this. So that the partial derivative of z with respect to x gives me the partial derivative of my function with respect to x, and in my notation I can write that as fx, where the x is written as a subscript. If I wanted to take a derivative holding x fixed and letting y change, I will get the partial derivative of z with respect to y, which is equal to the partial derivative of the function with respect to y, which is equal to fy. The partial derivative of f with respect to x at the point AB is formally defined as fx of AB is given by the limit as h approaches 0 of f of a plus hb minus f of ab divided by h. The partial derivative of f with respect to y at the point AB is given by the limit as h approaches 0 of f of a and b plus h minus f of ab over h. This is provided those limits actually exist. The notation can vary depending on the source. I could have fx of ab, I could have partial derivative notation where it looks like a little backward 6 of f over a little backward 6 of x evaluated at the point AB. This is just equal to the partial derivative of f with respect to x, written using the little backward 6 on top and bottom of AB. If it's y, I use a subscript of y and take the partial derivative of f with respect to y at the point AB, or I can write it as the partial derivative of f with respect to y of AB itself. F sub x or fx and f sub y or fy are both functions. F sub x of AB or f sub y of AB are function values at the point AB. So if I just have the fx and the fy, it's just a function. But if I give you the points AB next to it, it's talking about looking for a function value. Let's work some examples. I want to find the first partial derivatives of each of the following functions. The first function is f of xy is equal to the quantity x squared plus 1 times e to the y. The second function is f of xy is equal to the square root of x squared plus xy plus y squared. For the first function, the quantity x squared plus 1 times e to the y, I take the partial derivative of f with respect to x, and I get 2x times e to the y. Notice that I take the derivative of the x squared plus 1 term and treat the e to the y term as a constant. The partial derivative of f with respect to y requires that I hold the x squared constant and then take the derivative of e to the y, and that's exactly what I'm going to do. I treat x squared plus 1 as a constant because y does not appear there, and I take the derivative of e to the y. I get the quantity x squared plus 1 times e to the y as the partial derivative of f with respect to y. For my second function, f of xy is equal to the square root of the quantity x squared plus xy plus y squared. Fx will be given by 1/2 times the quantity x squared plus xy plus y squared raised to the negative 1/2 power times 2x plus y. Notice that I have to use my chain rule here. I'm going to simplify that a little bit. I get the quantity 2x plus y over 2 times the square root of x squared plus xy plus y squared. My fy, partial derivative with respect to y, is given by 1/2 times the quantity x squared plus xy plus y squared raised to the negative 1/2 power times x plus 2y. Again, I simplify that a little bit. I get the quantity x plus 2y over 2 times the square root of the quantity x squared plus xy plus y squared. So now you get to try it. Pause the video and find the first partial derivatives of the function f of xy is equal to x minus y divided by x plus y. When you are ready, restart the video to check your understanding. To find the partial derivative with respect to x, fx, I have to use the quotient rule. This gives me the quantity x plus y times 1 minus the quantity x minus y times 1 over the quantity x plus y squared. This simplifies to 2y over the quantity x plus y squared. The partial derivative with respect to y, or fy, is given using the quotient rule by x plus y times negative 1 minus the quantity x minus y times 1 over the quantity x plus y squared, which reduces to negative 2x over the quantity x plus y squared. This is working with partial derivatives. We hold all but one of my independent variables constant and then take the partial derivative with respect to the variable that I am letting change. Let me know if you have any questions about this introduction to partial derivatives.